Hey everyone, welcome back to my Calculus 1 series. In today's lesson, we're going to be going over how derivatives affect the shape of a graph. So to start off the lesson, we'll go over the notion of increasing and decreasing functions. And if you remember from one of the first videos I made, an increasing function is when we take two x values, let's say x1 and x2, and the value evaluated at x2 is greater than the value evaluated at x1. Meaning the graph, if we were to draw it, looks something like this, right? Where this would be an x1 and then this would be an x2. So we could see that the value at x2 would be, in a sense, higher up or larger than the value at x1. Likewise, for decreasing, if we were to take an x1 and an x2, the value evaluated at x1 now is going to be larger than the value evaluated at x2. And we can think of that in a similar way where if we were to think of a graph, something like this, we were to take x1 here and an x2 here, the value evaluated at x1 being here will be larger than the value evaluated at x2. Basically, an easy way to think about it is if the function is increasing in values, meaning going upwards, it's increasing, and if it's going downwards, decreasing in values, it's decreasing. So now let's take a look at how slope affects this, specifically the slope of a tangent, or as we know it now, the derivative. So firstly, what I'm going to say is that if the derivative on an interval is greater than 0, then the function is increasing on that interval. So I'm going to write it down, and I'm going to show you why this is true. Like I said, if the derivative of the function is greater than 0 on an interval, then we say that f is increasing, the function f. And the reason this is true is, again, if we look at a quick example of something like this, right? We know that this function is increasing because if we were to evaluate an x1 and an x2, the value at x2 is larger than the value at x1. But what we can also notice is that the tangent right here, the tangents of all of these points actually, the tangents all have a positive slope. So we know that if the tangent has a positive slope, then it's kind of leaning from the third quadrant over to the first, or kind of going from left to right in a sense. And that's exactly what's happening in this graph right here. So these straight lines that I've drawn are the tangents. Sorry, they're freehand drawn, but they're supposed to show the tangents of the graph at those values. So if the tangent is has a slope that is greater than 0, then we can say that it's increasing because it's going from left to right. So the values will be increasing as x increases. And we can say the opposite. If f prime at x is less than 0 on a specific interval, then f would be decreasing on that interval. And again, just to show you, if we had a decreasing function like this, the tangents would go something along the lines of these. And we can see that now the tangent is going from the second quadrant right here to the fourth quadrant over here. And it's kind of going from the top left down to the bottom right. And the slope of these tangents is actually going to be negative. So we're going to have a negative slope, and a negative slope would mean that it's less than 0, and that would mean that the function is decreasing on that interval. So just a quick example as to how we can apply what we just learned. Let's say we were given the derivative of a function, which is right here. And the question asked us to find all the intervals of increase and decrease. So we can do that by just doing what we know. So let's first factor out everything we can to get it in simplest terms. So there's the function in simplest terms, and we can see now that the zeros, if we were to set this equal to 0, the zeros of this function, or the x-intercepts, would be that x is equal to 0, x is equal to 2, and x is equal to minus 1. If we quickly draw a number line and kind of just plot these values where they are, 0 would probably be somewhere here, minus 1 would maybe be somewhere there, and then 2 would probably be somewhere there. Obviously this is not to scale, but it's just to get a quick representation of what's going on. So now if we were to take a value between 0 and 2 right there, let's take something like 1. If we were to plug in f prime of 1, we can easily get the sign of the derivative between that interval. And all we have to do is plug in a value between this interval right here, and then the function, the f prime function, will give us the value of the slope of the tangent there. So if we plug in f of 1 right now, we're going to get 12 times minus 1 times 2. So this right here is going to be minus 24. But we don't really need to compute all this. We just need to make sure that it's negative or positive. So because we had the derivative function right here give us a negative value, that means that the slope on that interval is decreasing. So we can say that the function here is decreasing. Now if we were to do the same for every interval, we could find out in exactly what intervals the function is increasing or decreasing. So here is the first derivative test. Now we would use the first derivative test alongside the the increasing and decreasing test that we've seen before. However, the first derivative test is kind of going to build on top of that. It's going to introduce a couple new features of the graph. So the first bullet point of the first derivative test is that if f prime changes from positive to negative at c, then f has a local max at c. And I'm going to go through these one by one right now, just kind of reading them so you understand what we're talking about, and then I'll demonstrate to you graphically as to why these make sense. So to continue, the second bullet point that we're going to be going over is that if f changes from negative to positive at c, then f has a local minimum at c. And the last point is that if f prime is positive to the left and right of c, or it's negative to the left and right of c, then f has no local min or max at c. So we can see that the difference between the first derivative test and the increasing or decreasing criteria that we learned before is that the first derivative test checks to see where the local min or local max are, as opposed to finding intervals of increase or decrease. So here I've drawn a couple of functions that we're going to be using to demonstrate the first derivative test. And if we analyze the first point, which is right here, of the first derivative test, we can see that f prime, saying that f prime changes from positive to negative at c, then f has a local max at c. Let's say here is c, right? Let's say this is the value of c. And we're saying that if it changes from positive to negative at c, then f has a local max. And if we look at it, this is exactly true, because if the slope of the tangent is going from positive, right, and it's eventually changing to a negative slope, that means eventually we have reached a point where the slope has transformed from something like this to a horizontal tangent, and then it's went in the other direction. So if we see that the slope was positive, meaning it was pointing from bottom left to upper right like this, and then we've changed it to a negative slope, meaning it's pointing from top left to bottom right now, we can kind of see how this would form something with a local maximum. Now on to the second point. If the slope changes from negative to positive at c, let's say c is here, then we say that f has a local min at c. So again, let's take a look at these slopes. They are negative, as we can see, going from upper left to bottom right, and then after that it changes from bottom left to upper right, and we could see how this would form a minimum value because we drop down and then eventually we go back up. So we would have a minimum value. And this last point can be shown in two scenarios. Basically, I'm going to break it down to the first half, like right before the comma here, and then right after the comma. So we're saying that if f is positive to the left and right of c, meaning that it has a positive slope or a positive tangent on both sides of c, let's say c is right here, as we can see here, we would have a positive slope, and then it would still be positive right here. That means if it hasn't changed, the direction of the slope hasn't changed, then there's no local min or max. We cannot say anything about this point right here. Likewise, if we were to take c to be right there, and we would look at the slopes, this has a negative slope right here. And as you can see, the slope after c does not change any direction. So again, we cannot say that it has a local min or max. And it actually makes sense because this point right here in the middle is neither a min or a max. The min would be would actually keep on going forever, and then the max, we it would keep on going forever as well in both functions. So this one and this one. So C is not a min or a max. That's all these things say. So again, if we change from positive to negative slope, that means that we've hit a local max. And if we've changed from a negative slope to a positive slope, that means that we've hit a local min. So now moving on to second derivatives. Previously we were talking everything about first derivatives and how they affect the shape. Now we're going to be moving on to second derivatives. And here is one thing to note about second derivatives. If the second derivative of a function is greater than 0 for all x on an interval, then the graph is concave up. In case you forgot what concave up means, it means like this, so that it's, the way I remember it is it's kind of opening up upwards. And likewise, if it is less than 0 for all x on an interval, then it is concave down. And concave down is like this. It's opening up downwards. So this leads us into the definition of an inflection point. And a point P on the curve y equals f of x, so it's important to note that it's actually on the curve. We call this point P an inflection point if f is continuous there and the function or the curve changes concavity from either concave up to concave down, or from concave down to concave up. Once we hit that point, it would look something like this, right? So before, right on this interval right here, we were concave up, and then all of a sudden on this interval we're concave down. So the inflection point would be somewhere around here. And lastly, this brings us to the second derivative test. So likewise with the first derivative test, when you're testing for local maxes or mins, the second derivative test does a similar thing, except we kind of build on it and we use the concept of concavity to kind of show why something is a local max or a local min. So the 2 points for the second derivative test are that if f prime at c is equal to 0, meaning that this is a critical value, and f double prime at c is greater than 0, then f has a local minimum at c. The reason we say that it has a local minimum at c is, if you remember from the definition here of the second derivative, if right here, if f of x is greater than c, then the graph is concave up on that interval. So if we look at a concave up function, right, it goes something like this. And we know that if it's concave up, then we're likely to be down here again, because it's a critical value, meaning the slope of the tangent here is horizontal. But on top of that, we're concave up, meaning there's no way that this can be a local max. And likewise for this last point, it's that if, again, we're at a critical point, meaning f prime at c is equal to 0, and f double prime at c is less than 0, then f has a local maximum at c. And the reason for this being is quite similar. If we remember from the definition here, if f double prime at x is less than 0, then the graph is concave down. And a concave down function would look something like this. And this must be c right here because it's a critical value, meaning the slope of the tangent is horizontal. And from here we know that the function, or sorry, this point must be a local max because it is a critical value, and on top of that it's concave down on this interval, so it must be a local maximum. So that's it for today's video on how derivatives, specifically the first derivative and the second derivative, kind of tell us different things about the shape of the graph. Hopefully you enjoyed today's video. If it's helped you out at all, please like and comment as to what it helped you out with. Like usual, if you are new to this channel, please like, comment, and subscribe. It's greatly appreciated. And yeah, I will catch you guys in another video.